Because of the conditions described by Tobler's first law, spatial dependence is pervasive in geographic data. So there's almost always going to be a relationship between neighboring observations, and we just have to deal with that. But there's another problem, known as spatial heterogeneity. So in the sciences, we generally assume that samples are being taken from homogeneous populations. That is, the entire population is essentially the same, so we can take samples from it and establish an average that is similar to what we would expect to represent the entire population because they're reasonably similar. However, Earth's surface is highly variable. There's no such thing as an average place anywhere on it. So even though things are related based on space, there's also considerable diversity and variability. And so this is known as spatial heterogeneity. Conditions in one region may vary considerably from those of adjacent regions. So for instance, I am sitting in Mount Pleasant right now, and it's about 18 degrees out and sunny, and it's very warm and it's nice. But if you go 15 kilometers to the north and go to the top of one of the mountains, there's still meters of snow on the ground. So even though all the vegetables in my garden are sprouting right now, and it's very obviously spring here, it's still winter up on the mountain, and that's only 10, 15 kilometers away. So this often makes it impossible to define a homogeneous population with regards to a spatial unit, for instance. So for a visual example, when you think of spatial homogeneity, think of a Christmas tree farm, or any farm field for that matter. You have uniformly planted vegetation that grows in nice, neat rows. All the species are the same. They're approximately the same distance apart. It's fairly uniform. When you think of spatial heterogeneity, think of a natural forest landscape where you have a variety of different tree species that might vary with different co-founding factors, but also just going to be kind of randomly dispersed through the forest. You might have a birch next to a maple, next to an alder, next to a cedar. And so the natural world tends to have considerable spatial heterogeneity. Built environments tend to have a bit more spatial homogeneity, but again, you can't really always assume that things are spatially homogeneous just because they're built by humans. And how do we work around the problems associated with spatial data? How do we account for spatial autocorrelation, and how do we account for spatial heterogeneity? One option, if you want to stick to common statistical methods, might be to discard data until the proposition of independence becomes acceptable. So you would just remove the data until what remains are far enough apart that they can be regarded as independent. But this isn't a very good solution. Generally speaking, don't want to throw away data if you can avoid it. And further, in the geographic sciences, a lot of times we need to work with all the data that is available. Another option is to abandon inference altogether and instead rely on description. So instead of making any attempts to generalize about a larger population, you focus only on the study area using specific local statistics. So this is oftentimes a better solution depending on what you're doing. Generalizing is sort of the ideal. You want to take patterns that you see in one area and apply them and extrapolate them to other regions. But the heterogeneous nature of spatial data makes this difficult in some circumstances. One of the more common things that we tend to do in GIS is focus on pattern detection. So rather than trying to work around the issues with spatial data, we can try to exploit the issues with spatial data. So we can exploit the nature of spatial data to use that to recognize patterns, make observations about how those patterns differ from a random arrangement. Are the patterns observed likely to occur by chance? If not, what are the contributors to that detected pattern? So in this case, we might have a hypothesis being tested that explores the likelihood that conditions occurred by random chance. And if that fails, then those conditions are likely not random. There's something that set them up, caused something to happen. And finally, there's been significant research devoted to devising different versions of inferential tests that can cope with spatial dependence and spatial heterogeneity found in spatial data. Most GIS software already includes some of these packages, so there's plenty in ArcGIS Pro, for instance, and there's a whole field called spatial statistics. Now, the nitty-gritty details of spatial statistics are a bit beyond the scope of this course. I'm not going to delve too much into the specifics of spatial statistics. I'll leave that to upper level GIS courses, but it is important to know that there's a whole field dedicated to working around the issues regarding spatial data.